Dear students, in today's session, we will be discussing certain basics of Turing machine. Before discussing the Turing machine, we have already discussed two machine models. Those machine models are finite automaton. In finite automaton, we were having a finite state control which was able to read a fixed length input from left to right. As it reads a symbol from its input, then it changes the state. So through the change of the state, it remembers what it has read. So as the number of states in this finite state control are finite, so it is able to remember only the finite information and able to recognize only the regular languages. Okay. We have also seen some variants of this finite automaton. These were the NFA and epsilon NFA. So we have seen that these variants in the model of FAs does not add any additional computational power to the machine. They only provide some convenience in designing. Then to add some more power to it, what we have done, we have added a additional memory in the form of a stack to this finite state control. And then our model has become the PDA, which was able to recognize the context-free languages. As it is a more powerful model, it is able to recognize context-free languages and perform certain computations as well through the operations of push and pop over the stack. Okay, and then we have seen one more variant of this push down automata, which was having two stacks. So one more additional memory we have added, and then we have seen that some more power has been added to this machine model, and we were able to recognize certain languages which were not context free. Okay, so but we have seen that if we add additional memories, suppose 3 stack, 4 stack, 5 stack, it does not further add the power. So we can do whatever we want to do through the 2 stacks only. So these were the models which we have discussed. Now we will be discussing Turing machine model, which is able to recognize recursively enumerable languages. What a Turing machine model is, it is a simple mathematical model of a general purpose computer. So if we talk about the power of the Turing machine, so anything which is computable can be computed over this Turing machine. So meaning thereby any work, any computation which a general purpose computer can do can also be done on this Turing machine. Now we will be discussing its model, Turing machine model in detail. Now we will discuss our Turing machine model. In our Turing machine model, we have a finite state control as we were having in case of finite automata. So it is a similar kind of finite state control, which is having a read-write head, which is connected to a tape of infinite length. This is a tape of infinite length which is divided into cells, and each cell is capable of holding one symbol. Now this symbol may be the input symbol, or it may be some other symbol which we may store over the tape. Now over the tape in the cells, we may have a special symbol stored which is known as the blank symbol and represented by this hash symbol. In many different texts you may find different blank symbols. In many texts you will find this B as the blank symbol, or this B cutted by a line. This is also known as the blank symbol, or in some text you may find this symbol as the blank symbol. So different blank symbols are given into the different texts. Now we have to take any one of them. So we will be preferring to have hash as the blank symbol. Okay. So now we are having the finite state control which was connected to this tape, and this tape is used to hold the input string as well as every string which is the part of our processing. Like in case of PDA, we were having a separate memory in the form of a stack, where we were pushing certain things and we were doing the popping operations. So through the push and pop operation, we were performing our computation. Now in case of Turing machine, every computation is performed over this tape. Now this tape is of infinite length, so we can move in the left direction or we can move in the right direction. So we are having a read-write head here. If you remember, in FA and PDA both, we are having only the read head connected to the input. So we can only read from the input, we cannot write something there. Okay, so now here we can read and write both, and our input head can move either in the right direction or in the left direction, while in case of FA and PDA, from input we can only read and we can read from left to right. So this is the difference between the Turing machine model and the models which we have discussed previously, that is the FA and PDA. Now we'll look at how we will be processing a string, or how we'll be doing a move over the Turing machine. What will be done during a move in the Turing machine? So during the move of a Turing machine, we will take the current state. Suppose we are in the current state queue, and then we will take a symbol from the input tape. Okay, so from this tape, from the input, we will be reading one symbol. Basically, we will be reading a symbol under the read write head. Suppose my read write head is indicating to this cell. So whatsoever is stored in this cell, I can access that. So that will be input for me. So suppose in this case it is A2. So Q and A2. So what will be this delta Q and A2? What it will take? So these two will be the inputs, and on the basis of these inputs, your Turing machine will take certain actions. What are these actions? These actions are in the form that what will be the new state of this finite state control. So means what new state I am moving. Suppose it is P. Okay. Then I will decide what I should write in the cell under the read write head. Means I can modify this cell. Okay. So suppose in place of this A2, suppose I choose to write some other symbol C. Okay. So I will be writing C here. Okay. Then third thing is, in which direction my read write head should move. Whether I should move towards the right or I should move towards the left. So it may be either R or L. So suppose I am moving towards right, so I will be writing R. If suppose I want to move my head, read write head towards left, then I will be writing L here. So this will be the format of a transition in a Turing machine. So in each machine, we will take current state and the current input symbol, and on the basis of these three things we will change. And then one fourth decision also has to be taken, whether machine should halt or not. Whether machine should halt or not. If you remember, in case of FA and PD, in case of FA, there is no concept of halt. Machine will halt only when your input string is fully processed. Even in the models where we were having the non-determinants, that is an FA or epsilon and FA, we are having a concept of input cache. So without reading the string completely, if we reach to a situation where we do not have any move, we don't know what to do. So in such case, our machine halt. In PDA, because PDA is non-deterministic by nature, so always PDA halts when our stack associated with PDA is empty. So those were the predefined conditions in which your machine is going to halt. So decision of halt has not to be taken by the machine, it will be the automatic one. Now here machine will take the decision whether to halt or not as per the definition given in the transition function. So we'll discuss in detail how we can write or we can represent the transition function in the Turing machine. So we'll discuss further details of the operation of the Turing machine and its formal definition, how we can formally define a Turing machine. From this now you would have understood that what do we mean by the Turing machine model and how this model works. It will basically take two inputs, a state, current state, and the current input symbol under the read write head, and then it will decide the new state, what is to be written in the current cell, and where to move, whether we have to move towards the right or towards the left, and then whether to halt or not. Our Turing machine is defined as M is equal to Q sigma tau delta Q0 hash and F. It is a 7 tuple because 7 things are there. Now we'll one by one discuss what these quantities mean. So capital Q, we already know that capital Q is a finite non-empty set of states, as in case of FA or as in case of PD. Then tau. This tau is is again a finite non-empty set of tape symbols. So it consists of this tau. It consists of all the symbols which we can store in in a cell of our tape. So whatsoever we can store over the tape, that will come in the set of tape symbols, that will be the part of tau. Then this hash, this we have already defined that it is a blank symbol. So hash is a blank symbol, and this belongs to tau because this we can store over the tape. So it is one of the tape symbols. So hash belongs to tau. Then sigma, it is finite non-empty set of input symbols as in case of FA and as in case of PDA. And this sigma will be a subset of tau because all input symbols we can store over the tape as well. So that's why sigma will be a subset of tau. Okay, so all the symbols which are the input symbols will also be the tape symbols. And hash, that is the blank symbol, does not belongs to sigma. So our blank symbol cannot be the part of input alphabet. That will be only the tape symbol, but it will not be the part of input. It cannot be the part of input alphabet. Okay, we can take certain decisions over this blank symbol, but we will not assume it as a input. So Q0 is the initial state, as in the case of FA and PD as well, and F is the set of final states as in case of FA, and this set of final state, because it is a set of states, so it is a subset of capital Q. So it comes from the set of all states. So F will be a subset of Q. Now only thing which we have not defined is the transition function delta. So now we will discuss what the transition function delta is. The transition function delta of our Turing machine, it simply maps the states of finite state control and the tape symbols to the states, tape symbols, and the movement of read-write head. That is, our transition function delta is from Q cross tau to Q cross tau cross L comma R. So it will tell us what to do for each state and for each input tape symbol. Okay, and the nature of this transition function delta is deterministic because corresponding to each combination of a state and the tape symbol, we will be having only one choice. So we will be having only one output. So it will clearly tell us to what state next we should reach, what symbol we should write in the current cell, and where we should move, whether we should move left or we should move right. So it will clearly tell us. And in some of the cases, for some of the combinations of the state Q and the tape symbol from tau, we will not be having this function defined. So in all such cases, our instructions will be halt. So in such cases, we will be halting. So in each case, whatsoever combination of state and this tape symbol we are having, either we know what to do or we have the instructions of halting. So for each combination, we are having only one choice. So that's why the nature of this transition function delta is deterministic. That's why our Turing machine by default is a deterministic machine. Now we will discuss how we can represent a Turing machine. We can discuss our Turing, we can represent our Turing machine basically by three methods. Number one is through the instantaneous description, or in short, we can call it as ID. Second is the transition table, and third is the transition diagram. Among these, the first one, in this we will make use of the move relations, and this description will tell us the current status of a Turing machine in action, while the transition table and transition diagram representation will tell us what our Turing machine as a whole works. So now we will be discussing these representation methods in detail. As I have already described, that ID is used to describe the current status of a Turing machine in action. So if our Turing machine is in action, then what is the current status of that machine? This ID will be used to describe that. We will also call this as the snapshot of a machine. Okay, so this is also called as the snapshot of a machine. How do we define this snapshot or ID? This snapshot or ID is defined with the combination of two things. Number one is the current state and number two is the entire string. If you remember, we have also discussed ID in case of push-down automata. In case of push-down automata, our ID was the combination of three things. Number one, what is the current state? Number two, the input string remained to be processed. So whatsoever part of the input string we have processed, that we will not take into count. We will only take into count the remaining part of the string which is not processed up till now. And then the status of the stack. So this was the ID for PDA. But in case of Turing machine, we do not have any stack. So no status of a stack is required. We are having only the tape where our string is stored. Okay. And then then a finite state control. So the current state. Okay. Now why we have taken the entire string, not the string which is remained to be processed? Because in Turing machine, we can move our read-write head can move towards the right as well as it can move towards the left. So in both the directions, our read-write head can move. So that's why we have to always take the entire string as the part of the status of the current status of the machine. So that's why we will take current state and the entire string. Now with this example, it will be more clear to you. Suppose this is the situation of the tape of a Turing machine under action. Okay, so left to it, we are having only the blanks, and right to it, we are also having the blanks. So our input string is starting from here, and it is up to there. It is not input string; it is the string stored over the tape during the processing. Okay, so starting from here, we have processed the symbols up till now, and at present, we are going to process this the symbol is stored in this particular cell. Okay. Now our current state is Q3. So in this manner, our ID or snapshot will be of the form alpha, beta, gamma. So ID will be in the form of alpha, beta, gamma, where beta will be the current state and alpha, gamma will be the whole string. Okay. So alpha is the left part of the string. The part of the string which is towards the left of the read-write head, and gamma is the part of the string which is towards the right of the read-write head, with the first symbol of gamma under the read-write head. Okay, so in this manner our IDs, it is alpha, beta, gamma. So if we combine alpha and gamma, we will find the whole string, and beta will be the state. Okay. So string towards the left of the current read-write head will be A4, A1, A2, A1. So A4, A1, A2, A1. So this is my alpha. So up till now, I am having my alpha. And starting from here up to the last, it will be the gamma. So gamma will be A2, A2, A1, A4. A2, A2, A1, A4. And this A2, the first symbol of the gamma, it is the symbol which is currently under the read-write head, means the symbol which we are going to process. And Q3, this state is the current state. So in this manner, we can define our Turing machine in action through the ID or through the snapshot. So whenever we have to show the processing of a particular string over the Turing machine, we will take help of the IDs. From one ID, we will be moving to the another ID as per the transition function delta. So basically, processing of a string over the Turing machine is nothing but just the movement of IDs. From one ID, we will move to other ID. From that ID, we will move to other ID. In this manner, we will keep on moving between the IDs until our machine does not halt. Now I am going to discuss what do we mean by a move in a Turing machine. So suppose delta Q xi is equal to PYL. This is one transition. Okay. So we are currently in the state Q, and xi is the symbol under the in the cell and which is under the read-write head. Okay. And then the next state will become P, and in place of xi we will be writing Y, and our read-write head will move towards left. So suppose this is our transition. So before this transition takes place, our ID will be x1, x2 and so on up till xi minus 1, q, xi, xi plus 1 and so on, xn. Suppose x1 to xn, there is the string, okay, and in that string our read-write head is on the cell which is indicating the symbol xi, okay. So that's why our this will be the part of gamma, okay. So xi will be the first symbol of gamma, and q is the current state, so q will come here, and before x1 to xi minus 1, the string which is before the xi will come before this state. So this will be our ID. Now when this transition takes place, so what will be the new ID? So if this transition takes place, this q will become p, so our state will become p, okay. And then because we have to move one position left, okay. So xi, before xi we will be having xi minus 1, so now xi minus 1 will become the cell which is under the current read-write, head, okay. So that's why xi, x1, x2 and so on, xi minus 2, up till now there will be no problem. And then the read-write head will come to the xi minus 1. So, and now because state has been changed from q to p, so that's why we have written p here. So now our state has come before the xi minus 1. So this will be the status. So up till xi minus 1 we are here, and because in place of xi, during this transition, in place of xi we have written y. So in place of xi we will write y, and the remaining string after this xi will be the same. So xi plus 1 and so on up till xn. So xi plus 1 and so on up till xn. So in this manner, this transition will force the move of this ID to this ID, and again the symbol for the move relation will be the same as we have discussed in case of PDA. Now suppose in place of L, suppose R is there, okay. Suppose PYR. So what should have been the new ID? So ID before this transition takes place will be the same one, okay. Now what we are declaring, in place of Q we will be writing P, in place of Xi we will be writing Y, and we have to move one position right. So we have to move one position right. So Xi is the current symbol under the read-write head, then Xi plus 1 will become the current symbol under the read-write head. So up till Xi, whatsoever it is up till Xi, that will come before the state, okay. So we are going to write this x1, x2 and so on up till xi minus 1, that is as it is. In place of xi we will be writing y, and then we will be writing p, okay, because now xi plus 1 has to be the current symbol under the read-write head. So xi plus 1 will be here and so on up till xn. So this will be the new ID. So we have seen how we can convert our transitions into the movement of the IDs. Now we will discuss the transition table representation of a Turing machine. So here I have made a example Turing machine. It's a transition table. So it will be almost similar to the transition table of a finite automaton. So here on this leftmost column we will be having the present state, and then the rest of the columns will be divided into the symbols which will be the tape symbols. So suppose my tape symbols are A, B and blank, okay. So I have made 3 columns for each tape symbol. So here I will be writing states, and among those states I will be marking which state is the start state and which state is the final state, okay. And then suppose I am having a transition function delta q1a to q2bl. Then if I am having such a transition function delta, then simply I will be writing q2bl under the column a along the row of the state q1. So row of the state q1 is this, and column of the symbol a, tape symbol a, is this. So in this cell I will be making this entry q2bl. So q2bl. So this entry I will simply make here. Means I will be telling what should be the next state, what should be written in place of this current symbol A. Okay, so B has to be written, so B will come here, and then I will tell whether read-write head should move towards left or right. So this entry will come here. So similarly, I will be making all the entries. Now you are looking here, this entry is blank. So this entry is blank simply means we are having a halt instruction there. So it may be written or it may not be written. So if a cell is empty, it simply means we are having a halt instruction there. So if we reach to such a situation, our Turing machine will halt. So suppose we are in the state Q2 and we are getting a symbol blank, then we will be halting. We don't know what to do in that particular case. So we don't have to take any action. We have to simply halt the machine. Our machine will halt in that situation. So in this manner, we can define a transition table corresponding to a Turing machine. Now we'll be discussing how we can represent Turing machine using the transition diagram representation. Now we will discuss transition diagram representation. Again, suppose we are having the transition function delta Q1A is equal to Q2BL as in the previous example. Then it simply means there is a transition from the state Q1 to the state Q2 over the symbol A. And in place of the symbol A, we have to write the symbol B, and then we have to make the movement of the read-write head towards the left. So Q1 is the state. In the circle, we will be showing the state. And then Q1 and Q2, these are the states. And from Q1 to Q2, there is a transition. Now, over this transition will be shown by the arrow, and these will be labeled as triple ABL. So A first quantity shows that Q1 on A moves to Q2. And then in place of A, we are writing B, and then read-write head movement is towards left. So we will be writing, we will be labeling this transition by this triple ABL. So ABLL, through this transition, through this triple, I will be replacing this transition. Okay. In some of the text, you may find in place of this comma, you can find something like this A oblique B comma L. So it simply means over A there is a transition. In place of A, you are writing B, and then read-write head movement is towards left. And in some other books, you can find A arrow B comma L. So this is also having the same meaning, that in place of A, we will be writing B, and read-write head movement is towards left. So any of these leveling you can use. I will be preferring to use simply A comma B comma L. So this triple. So first one is A, over which we are having the transition. B will be written in place of A, and this will show the movement of the read-write head. So in this manner, corresponding to each transition, we can make a figure in the transition diagram. So again, if you look at it, is similar to the finite automaton. From one state to another state, we are having the transition. In the finite automaton, we were having the transition level as input symbol only, suppose on A only. Here we are having the what will be the input symbol, what we are reading, then what we are writing, and then what is the movement of the read-write head. So all these three information are coming as the level. This is the only difference. Otherwise, it is almost similar to the finite automaton. Now we will discuss what is the language accepted by the Turing machine. Whether a given word W will be accepted over the machine or not. So suppose M is equal to Q sigma tau delta Q0 hash F. It is a Turing machine. And a string W which belongs to sigma star is said to be accepted by the machine M. If we say that W is accepted by M, it simply means that W belongs to the language of the Turing machine. Okay. It is in the situation when Q0W moves to. Now you see the symbol, this is the symbol for moves to, and this is an ID. If you look at, this is the initial ID Q0W. Our ID in case of Turing machine is of the form alpha, beta, gamma, where alpha is the string towards the left of the read-write head, and gamma is the string towards the right of the read-write head, and beta is the state. Now initially, the whole string will be towards the right side of the read-write head, because we will start processing our string from the very first symbol. So Q0 is the initial state, and read-write head is at the first symbol of the W. So whole W is towards the right side of the read-write head. So Q0W, it is a initial ID. So initial ID moves to. This is also the ID alpha 1, P alpha 2. So where alpha 1 and alpha 2 are belonging to tau star. So these are the strings. These are the part of the strings stored over the tape. So something is stored towards the left of the state, something is stored towards the right of the state, and P is the current state. So alpha 1, so basically alpha, beta, gamma, we reach to a ID of this form, where P belongs to F, means P, the current state, is a final state, and M halts in that particular case, then we say that string W is accepted over the given machine, and it is a part of the language defined by the machine. Our string W will not belong to the language of the Turing machine if either M does not halt or M halt in a non-accepting state. So if M is halting in non-accepting state, so machine is halting, but it is halting in non-accepting state, so that's why W will be rejected. It is similar to the acceptability definition of the finite automaton. In finite automaton also, when we reach to when our input string is fully processed, so there is no concept of fully processing of the string. Okay, there is the only concept of that we reach to a final state and machine halts. There also machine was halting, but that was halting after the full processing of the input string. So if it was halting in a final state, then string was accepted. If it was halting in a non-final state, then string was rejected. In the similar manner, if our machine is halting in a final state, then string is accepted, and if machine is halting in a non-final state, then string will be rejected. String will also be rejected if machine does not halt. Okay, so that is also the another situation that defines some categories of the languages that we will be discussing later on. So our string will be accepted only in the case when we reach to a final state and our Turing machine halts. So this is the situation, this is the condition for getting a string accepted over the Turing machine. In all other cases, our string will be rejected. And these are the two cases when our machine is halting in a non-final state or our machine is not halting, then our string will be rejected. So this was all I wanted to discuss in the basics of the Turing machine. From the next session onward, we will be discussing how to design Turing machine corresponding to a given language or corresponding to a certain action, how to perform certain computations over the Turing machine. That we will be discussing in coming sessions. Thank you all.